Attention deficit hyperactivity disorder, also known as ADHD, is one of the most common mental disorders, affecting 8.5% of children worldwide. Originating in childhood, its symptoms include inattention and hyperactivity, affecting a child's academic performance and self-esteem.
In Hong Kong today, a child's ADHD diagnosis can take from several months to over a year. During the wait, valuable time for early intervention is lost. It can also cost from 100 HAD in public centers to over $10,000 in private clinics, placing a financial burden on low-income families.
Hence, our team developed NeuroFocus, an affordable and efficient AI-powered diagnostic system using EEG and EOG signals to identify ADHD-related patterns in the brain and eyes. Let's see how it works.
Every thought and movement in the brain generates tiny electrical impulses, summed together as brainwaves that can be detected at the scalp. These oscillations have different frequency bands, with theta waves ranging from 4 to 7 Hz. These are linked to a state of inattention and drowsiness, while beta waves from 13 to 30 Hz are linked to alert, focus, and attention. These are measured through an EEG, or electroencephalogram test. Multiple studies show that individuals with ADHD tend to have an elevated theta to beta ratio.
An EOG test, or electrooculogram test, is used to identify eye movements by recording voltage differences between the cornea and retina, also known as cornea retinal potential. Eye movement changes in this measurement with slower reaction times and more erratic eye movements indicate ADHD signs.
In our design, we have implemented a biosensing tool called OpenBCI that measures both EEG and EOG data. The fabric cap holding the OpenBCI hardware will be placed on the user's head. An electrode will be placed at the CZ position, the midline central point, records activity from surrounding cortical areas.
Reference electrodes at both ears A1 and A2 provide a quiet electrical baseline to eliminate body noise. These electrodes detect voltage fluctuations produced by synchronized firing of pyramidal neurons near the cortex surface. At the same time, 2 electrodes near the eyes measure the corneal retinal potential, the steady voltage difference between the positively charged cornea and the negatively charged retina. The user has to complete 2 tasks, a resting state test and an oddball paradigm task. The resting test provides baseline oscillatory data for EEG and EOG, while the oddball test examines neuroreactivity, captured through event-related potentials like the P200 wave, which reflects attention and sensory processing.
The raw EEG and EOG data will then be transmitted to our software through our OpenBCI hardware. Once collected, our AI model filters the signals through a 1 to 50 Hz bandpass to isolate neurophysiological activity, and a 50 Hz notch filter to eliminate electrical power noise. Eventually, we get a signal that looks a little bit like this, which is a lot cleaner than usual. From these clean signals, our model then extracts the following statistical features. From the EEG, we extract the theta-beta ratio, power spectral density, spectral entropy, and standard deviation. And for our oddball data, we extract P200 wave delay and strength, as well as button press delay and its standard deviation. These features are then passed through a support vector machine with an RBF kernel, a robust classifier for nonlinear data. Finally, we perform a grid search for C and gamma to optimize our model, and then we use cross-validation to measure model accuracy, and we look at mean accuracy, standard deviation, F1 and range and F1 score. This ultimately allows for strong accuracy and minimized overfitting. The data will then be processed and analyzed by our AI-powered algorithm, which is based on past studies and primary data, which will then display the ADHD diagnosis.
During the development of our product, we conducted both primary and secondary research.
From our research, various past studies ranging from 2001 and 2014 identified a correlation between theta-beta ratio and ADHD indication with a 50 to 91% accuracy.
Our primary research was conducted through gathering 30 participants aged 6 to 18, with 25 non-ADHD participants as a control group and 5 ADHD participants as a target group. We asked them to undergo the same resting state and oddball tasks while collecting their EEG and EOG tests.
We utilized both our primary and secondary data as baselines to set specifications for our learning machine algorithm, allowing our model to recognize if an input belongs to the target or control group, thus producing an accurate diagnosis for any user using our model.
Through AI and open source tools for biosensing, NeuroFocus turns raw neural activity into actionable insights, allowing for early and accessible ADHD screening.
Simple, safe, and reusable, it bridges the gap between neuroscience, well-being, and families in need.